Inspect all connections in the panel, including the main breaker, branch breakers, and neutral bus. Tighten any loose connections and clean any corrosion. Use a multimeter to check the neutral circuit for continuity and proper grounding. Ensure that the neutral bus is securely connected to the grounding system. Visually inspect the wires running from the panel to the outlets and fixtures. Look for any damage, kinks, or loose connections. Use a ground fault circuit interrupter, or GFCI, tester to check for ground faults on the affected circuits. A trip GFCI indicates a ground fault, which can trigger breakers. Repeat voltage drop measurements using a more accurate meter or data logger. Ensure that the voltage drop does not exceed 5% under load. If all the above steps do not resolve the issue, consider contacting the utility company. They can investigate potential problems on their side, such as power surges or neutral problems. Ghosting is a highly unlikely cause of the problem. Check the phasing of the electrical system to ensure that all three phases are properly balanced. Install a power quality analyzer to monitor harmonics, which can cause tripping issues. Calculate the total load on the electrical system to ensure that it does not exceed the capacity of the panel and service. Firstly, check for loose or corroded connections. This involves a detailed inspection of all connections within the electrical panel. Pay close attention to the main breaker, which is the primary point of connection for the entire electrical service. Also, examine the branch breakers, which distribute power to individual circuits throughout the building. Finally, thoroughly inspect the neutral bus, which serves as the common return path for electrical current. When inspecting these connections, use appropriate tools to tighten any that appear loose. Loose connections can create resistance, leading to heat buildup and potential breaker trips. Additionally, carefully clean any corrosion that you find. Corrosion can impede the flow of electricity and cause similar problems. Secondly, verify the neutral circuit. The neutral circuit is a critical component of any electrical system. It provides the return path for electrical current and ensures proper voltage balance. To verify the neutral circuit, use a multimeter to check for continuity. Continuity refers to the presence of a complete and uninterrupted electrical path. If there is no continuity, it indicates a break or disconnection in the neutral circuit. Also, use the multimeter to check for proper grounding. Grounding is essential for safety as it provides a low resistance path for fault currents. Ensure that the neutral bus is securely connected to the grounding system. A loose or faulty connection can compromise the safety of the entire electrical system. Thirdly, inspect the branch circuit conductors. The branch circuit conductors are the wires that run from the electrical panel to the outlets and fixtures throughout the building. A visual inspection of these wires is crucial for identifying any potential problems. Look for any signs of damage, such as cuts, abrasions, or melted insulation. Also, check for kinks or bends in the wires, as these can create stress points and lead to future failures. Finally, inspect the connections at both ends of the wires to ensure that they are secure and properly tightened. Fourthly, test for ground faults. A ground fault occurs when electrical current accidentally flows to ground through an unintended path. This can be caused by damaged insulation, faulty wiring, or defective appliances. To test for ground faults, use a ground fault circuit interrupter or GFCI tester. This device is designed to detect even small amounts of current leakage to ground. If the GFCI tester trips when connected to a circuit, it indicates the presence of a ground fault. Ground faults can be dangerous and can also cause breakers to trip. Fifthly, measure voltage drop. Voltage drop refers to the decrease in voltage that occurs along a conductor due to resistance. Excessive voltage drop can cause appliances to malfunction, lights to dim, and breakers to trip. To measure voltage drop, use a multimeter or a dedicated voltage drop tester. Take measurements at various points along the circuit, both under load and without load. Ensure that the voltage drop does not exceed 5% of the source voltage. If the voltage drop is excessive, it indicates that the conductors are either too small or too long for the load they are serving. Sixthly, contact the utility company. If you have exhausted all of the above troubleshooting steps and the breaker tripping problem persists, it may be time to contact the utility company. The utility company is responsible for maintaining the electrical infrastructure up to the point where it enters your building. They can investigate potential problems on their side, such as power surges, voltage fluctuations, or neutral problems. In addition to the above steps, there are several additional considerations to keep in mind when troubleshooting breaker tripping problems. First, consider the possibility of harmonics. Harmonics are distorted waveforms that can be generated by electronic devices, such as computers, variable frequency drives, and LED lighting. Harmonics can cause a variety of problems in electrical systems, including breaker tripping, overheating, and equipment malfunction. To monitor harmonics, install a power quality analyzer. This device will measure the levels of various harmonics in the electrical system and identify any potential problems. Second, calculate the cumulative load on the electrical system. The cumulative load refers to the total amount of power being consumed by all of the electrical devices in the building. It is important to ensure that the cumulative load does not exceed the capacity of the electrical panel in service. If the cumulative load is too high, it can cause the main breaker to trip. To calculate the cumulative load, add up the power consumption of all of the electrical devices in the building. This information is typically found on the nameplates of the devices. Third, check the phasing of the electrical system. Phasing refers to the way in which the three phases of electrical power are connected. If the phases are not properly balanced, it can cause voltage imbalances and breaker tripping. To check the phasing, use a phase rotation meter. This device will indicate whether the phases are connected in the correct sequence. Fourth, consider the possibility of ghosting. Ghosting refers to the phenomenon of breakers tripping for no apparent reason. This is a highly unlikely cause of breaker tripping problems, but it should not be completely ruled out. Ghosting can be caused by a variety of factors, such as electromagnetic interference, static electricity, or even paranormal activity. If you suspect that ghosting may be the cause of your breaker tripping problems, try isolating the affected circuits and monitoring them for any unusual activity. Remember, safety is always the top priority when working with electricity. If you are not comfortable performing any of these troubleshooting steps, it is best to call a qualified electrician. An electrician has the knowledge, skills, and experience to safely diagnose and repair electrical problems. By following these troubleshooting steps, you should be able to identify and resolve the cause of your breaker tripping problems. This will help to ensure the safety and reliability of your electrical system. When dealing with the sore trip in the breaker, the fact that a 100-foot extension cord resolves the issue offers a vital clue. The extension cord adds resistance, limiting the inrush current. The problem likely lies in a combination of factors including the inrush current of the sore motor, the length of the branch circuit wiring, and potentially a slightly undersized breaker. Inrush current is the high initial current drawn by a motor when it starts. This surge is significantly higher than the running current and can easily trip a breaker if the circuit isn't properly sized. The 150-foot distance to the outlets from the panel exacerbates the voltage drop issue. Longer wires have more resistance, leading to a greater voltage drop under load. A 116-volt reading under load is borderline unacceptable and contributes to the breaker tripping. Standard voltage drop recommendations suggest keeping voltage drop under 3% for branch circuits. The fact that other breakers are tripping for seemingly no reason suggests a more systemic issue, rather than problems isolated to single circuits. Random tripping is often indicative of a neutral problem. A loose or corroded neutral connection can cause voltage fluctuations and imbalances, leading to breakers tripping. The neutral carries the unbalanced current from the load. If the neutral connection is compromised, the voltage on different circuits can fluctuate wildly, especially under load. The fact that the problem doesn't seem to be phase-specific initially could mislead you. A poor neutral connection affects all phases. This is because the neutral is the common return path for all three phases in a 120/208 volt system. The symptom of the saw working with an extension cord is a classic symptom of voltage drop issues on the circuit. the extension cord adds more resistance. Therefore, it lowers the amperage and voltage just enough to prevent a breaker from tripping, which means voltage drop is the most likely culprit. A more precise measurement of the voltage drop is needed using a digital multimeter or a data logger. Check the voltage at the panel and then at the outlet while the saw is running. This will give you an exact voltage drop. Also, check the voltage at the panel itself while the saw is running. If the panel voltage is dropping significantly, this indicates a problem with the service entrance conductors or the utility supply. The fact that the saw only draws 10 amps running is not particularly high for a saw, but inrush current can be 3 to 7 times the running current. This means the inrush current could be as high as 70 amps, even if only momentarily. This is why the length of the cord changes everything. The breakers could be nuisance tripping. Nuisance tripping is when a breaker trips at less than its rated current. This can be caused by a faulty breaker, overheating, or vibration. Check the breaker's connections and look for signs of overheating. If the breaker continues to trip, replace it. Also, check the torque. Breakers have torque ratings and the lug, so check the breaker rating. Breakers will trip if they are not torqued properly. Also, with the lights tripping, verify the type of ballast used in the L-bay lights. Electronic ballasts can generate harmonics that can contribute to breaker tripping. Use a power quality analyzer to check for harmonics in the lighting circuits. High harmonic distortion can cause breakers to trip and can also damage equipment. Power quality analyzers are essential for troubleshooting electrical problems in commercial and industrial settings. They can measure voltage, current, frequency, harmonics, and other parameters to help identify the cause of the problem. In addition, regarding the air compressor and pressure washer tripping breakers, these are motors and have high inrush currents like the saw. This is likely the same problem that the extension cord trick fixes. If the other circuits barely show up on the amp probe, this is suspicious. This could indicate a problem with the amp probe itself or with the way the measurement is being taken. Clamp-on amp probes are sensitive to the position of the conductor and can give inaccurate readings if not properly aligned. It could also mean the load is not operating. If a load is not operating, then it might be tripping from a wiring problem that is creating a short circuit. Review the connections on those circuits. In addition, systematically test each circuit under load, one at a time. Turn off all other loads and then run a heavy load on the circuit to see if it trips. This will help you isolate the problem to a specific circuit. Document the results of each test, including the voltage, current, and time it takes for the breaker to trip. This documentation will be helpful for troubleshooting and for communicating with the utility company. If all else fails, contact a qualified electrician to perform a comprehensive electrical inspection. An electrician can use specialized equipment to identify and repair any electrical problems. It's crucial to ensure the electrical system is safe and reliable for the building occupants. Before contacting the utility, it's important to rule out any problems with the building's electrical system. The utility company will likely want to see that you have done your due diligence before they investigate. When speaking with the utility company, be prepared to provide them with detailed information about the problem. This includes the symptoms you are experiencing, the steps you have taken to troubleshoot the problem, and any relevant measurements. The utility company may want to send a technician to your building to investigate the problem. Be sure to cooperate with them and provide them with access to the electrical panel and other equipment. Remember to consult the National Electric Code, or NEC, for proper wiring methods, overcurrent protection, and grounding requirements. Compliance with the NEC is essential for ensuring the safety and reliability of the electrical system. Section 310.15 of the NEC covers ampacity tables for conductors. These tables provide the allowable ampacities of conductors based on their size, insulation type, and temperature rating. Section 250 of the NEC covers grounding and bonding requirements. These requirements are essential for ensuring the safety of the electrical system and for preventing electrical shock hazards. Section 210.20 of the NEC covers overcurrent protection requirements for branch circuits. These requirements are essential for protecting the conductors from overload and short-circuit conditions. Follow proper lockout/tagout procedures when working on electrical equipment to prevent accidental energization. To energize the circuit, lock out the breaker and tag it to indicate that it is being worked on. Verify that the circuit is de-energized before touching any conductors. Use appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools. PPE is essential for protecting yourself from electrical shock hazards. Consider having a professional load calculation done to ensure that the service is adequate for the building's current and future needs. An increasing business might require a load calculation. Check the panel schedule to verify that the breakers are properly sized for the loads they are serving. An undersized breaker can trip easily, while an oversized breaker can allow the conductors to overload.